recording. All right, so good evening, everybody. This is our Exam 5 review for statistics. This is the last test in the class, and basically this last test is kind of broken up into two parts. It's chapter 7 and 9. The chapter 7 material was the hypothesis testing stuff, and then the chapter 9 was the linear regression material. So we're going to kind of go in order as the test will go. And the very first couple questions ask us to identify the null and alternative hypothesis, and also to identify which one is the claim. Okay. So we want to figure out whether something is HO, the null, or whether it's going to be HA. And we're going to start off by kind of reading what they say. They say that the mean IQ of statistics teachers is greater than 120. So what's told to us is that the mean is greater than 120. A symbol of the form greater, less than, or not equal to, those types of strict inequalities, those will only ever be an alternative hypothesis. Okay? So the mean is greater than 120, it's going to be our alternative hypothesis, and because that was what's stated in the question, that makes the alternative the claim in this case. The null would just simply be the exact opposite statement. The opposite of greater than would be less than or equal to. So for this particular hypothesis test, we would say that the null hypothesis is that the mean is less than or equal to 120. The alternative hypothesis is the mean is greater than 120. And the thing that was stated in the context of the problem was the mean greater than, so that means that the claim was the alternative hypothesis for this one. So that's what we'd be looking for you to be able to do just for this one particular question. Write down the hypotheses, what's the null, what's the alternative, and identify which one of the two is the claim. One of the things that you can kind of keep in mind is that we have really 3 different tests that can be done for the null and the alternative. So you might have something like the mean could be greater than or equal to some number. The corresponding alternative would be that the mean is less than k. Okay? And whenever we're talking about the tailness of a test, the tailness is always determined by the alternative hypothesis. If you think of less than as being like left, so this would be like a left tail test. Another possibility could be that the mean is less than or equal to a value. The opposite of less than or equal to would be greater than. And this would be an example of a right-tailed test. If you think of greater than means go to the right. So that's our right-tailed test. And then the last type of hypothesis test we can run would be purporting that the mean is equal to a value. So that the mean equals, let's say, k. The opposite of equals to would be not equal. And if that's your alternative hypothesis, this is what we call a two-tailed test. The reason why it's referred to as two-tailed is that if something is not equal to a value, it can be not equal one of 2 ways. That means that it would either be less than k, or it would potentially be greater than k. So we get 2 possibilities. We get 2 tails in that scenario. But these are the 3 different cases you would have for a pair of a null along with the alternative hypothesis. The second thing to keep in mind as we're kind of working through it is if the question asks about the tailness of the test, that itself always comes from whatever the alternative hypothesis is. Does anybody have any questions on part 1? Okay, let's go ahead and look at the next one then. In question 2, it says, the dean of a major university claims that the mean time for students to earn a master's degree is at most 3.3 years. State this claim mathematically, and then identify which hypothesis the claim is. So again, it should always begin by trying to write down HO and HA. The statement at most. At most means that much or less. So this is saying that the mean is less than or equal to 3.3 years. right? So at most means what? That much or potentially less. Now, a statement of the form less than or equal to, that would absolutely be a null hypothesis. So the mean is less than or equal to 3.3, and because that's what was stated in the context of the problem, that means this time that the null hypothesis would be our claim. The alternative hypothesis is just the opposite of the statement. The opposite of less than or equal to would be strictly greater than. So the mean is strictly greater than 3.3 would be our alternative hypothesis for this one. They didn't ask for it, but if we were to have to say what type of tail test it is, well, because it is greater than means go to the right, this would have been a right-tailed test. If we look at the next question, in question 3, they actually give us the hypotheses. They say the null hypothesis is that the mean is less than or equal to 25, and the alternative hypothesis is that the mean is greater than 25. They simply want to determine what type of test is it. Is it left tail, right tail, or two-tailed? In order to answer that question, it's simply a matter of looking at what does the alternative hypothesis say. The alternative hypothesis says that mu is greater than 25. And again, if you're thinking of like your number line, the greater than numbers always go to the right. So this would be an example of a right-tailed test. Okay. So that would be a right-tail test. Does anybody have any questions on the first 3 problems? Let's go ahead and then take a look at the next batch. In question 4, they say that a brewery claims that the mean amount of beer in their bottles is at least 12 ounces. Determine whether this is a left tail, right tail, or a two-tailed test. In order to, excuse me, in order to determine that, again, we have to know what the hypotheses are. So we have one step to begin with. We need to set up our hypotheses. The claim is that the average amount is at least 12 ounces. At least means that much or more. So that would be translating to the mean is greater than or equal to 12, because at least means that much or more. So that's greater than or equal to. We don't need it for this problem, but that was what was stated in the context. So that's going to be our claim. The alternative hypothesis is simply the opposite of this. The opposite of greater than or equal to would be strictly less than. And now to determine the tailness, we just need to look at the alternative hypothesis. Because the alternative hypothesis contains the statement less than, if you think of your number line, less than means go to the left. So this would have been an example of a left-tailed test. Does anybody have any questions on that one? Let's take a look at the next one. In question 5, it says the Jedi claim that the mean lifespan for a Sith apprentice is at most 5.1 years. If a hypothesis test is performed, how should you interpret a decision that fails to reject the null hypothesis? Okay, so let's go through this again. With any hypothesis testing question, generally speaking, you always want to begin by stating what is the null, what is the alternative, and identifying which one of the two is the claim. When they say at most, that is going to translate to that the mean is less than or equal to 5.1. So the mean is less than or equal to 5.1, and because that's what was stated in the question, that means that the null is going to be our claim. The opposite statement of this would be our other hypothesis. The opposite of less than or equal to would be strictly greater than. And now the question then becomes, how should you interpret a decision that fails to reject the null hypothesis? Okay. So this is something that we saw in the homeworks. And when you go to do your conclusion for a hypothesis test, there's kind of like two different things that can happen. And the first part is the first part of the sentence. So when we go to write the conclusion, I'm going to spell conclusion. That never helps. Let's abbreviate it. The first part deals with the type of decision. So do we reject the null? Or do we fail to reject the null? If the conclusion rejects the null, okay, then the beginning of the sentence would be, there is sufficient evidence to. If we fail to reject the null, then the beginning of our conclusion sentence will be, there is insufficient evidence to. So insufficient means that there is not enough. So that's how the first part of your conclusion sentence will always go. And again, it's depending upon what decision that we ultimately make. When we reject the null, the conclusion sentence will start with, there is sufficient evidence to. And then if the conclusion was to fail to reject the null, then the beginning part of the sentence would be, there is insufficient evidence to. Now, the second half of our conclusion sentence depends upon which of the hypotheses was the claim. So if HO is the claim, then it will be to reject the claim. After all, a null hypothesis can never ever be truly supported. It can either be rejected or it can be failed to reject it. On the other hand, if the claim had been the alternative hypothesis, then the second half of our conclusion sentence would be to support the claim. So whenever you're trying to write up your conclusion for one of these hypotheses tests, the first thing you need to ask yourself is, well, what was the decision that was made? Did we reject the null, or did we fail to reject the null? If you reject the null, we start off with, there is sufficient evidence to. If we fail to reject the null, then it would be, there is insufficient evidence to. The second half of the sentence is based upon which of the two hypotheses was the claim. If the claim was the null, then it would be to reject the claim. And if the claim was the alternative hypothesis, then it would be to support the claim. So let's go back now to the one that we have. They said, how would you interpret a decision that fails to reject the null? Well, anytime we fail to reject the null, automatically the sentence is going to start off as, there is insufficient evidence. So there is insufficient evidence to. And now the second half of our sentence is going to be either to support the claim or to reject the claim. And that part of it depends upon which of the two hypotheses is the claim. Because the claim is the null hypothesis, the second half of the sentence will go to reject the claim. So 2, reject the claim. So this is how we would write our conclusion. So this is the answer. In the event that we fail to reject the null for this particular hypothesis test, our takeaway would be that there's insufficient evidence to reject the claim. Does anybody have any questions on that one? The next thing we get into is we're actually going to go ahead and run a hypothesis test. And so typically, if you're looking between 9.2 and 9.3, 7.2 and 7.3, it's kind of the same analogy as back when we did confidence intervals. If you remember back in chapter 6, where sometimes we use like a z interval, sometimes we use like a t interval. The same thing will be kind of true here, and that's that if we have a large sample size, we're going to be using what's called the z test. So if n is greater than or equal to 30, we're able to use the z test. And in the event that n is less than 30 and sigma is unknown, we'll be able to use the t-test. So first thing, that we're not doing the full hypothesis test for this. They only ask us to do the p-value, but let's start to get into some good habits here. Again, at the very beginning, we should at least state our hypotheses. So we want HO and HA. We're trying to test the claim that the mean is greater than 14. Greater than 14, that would be an alternative hypothesis. The opposite of greater than is less than or equal to. So the mean would be less than or equal to 14. And now we have this other summary statistics information. We know that the sample size is 50. That means we're going to be using a z-test in a minute. The sample mean was 14.3, and the sample standard deviation is 1.2. In order to find a p-value, which is the approach we used in our class for hypothesis testing, what you should do is hit the stat button. We're going to go over to the far right menu, which is tests, and we're going to use option 1, which is the z-test. Once again, you'll have a couple different options for input. If we were given the raw data set that consisted of all of the 50 different values, then we would put them in the L1 list and we would work off of the data tab. Here, they provide us with the summary statistics information. So we want to move over to the stats ribbon and hit enter to select it. The mu sub 0, remember that's the same value that's used in your hypotheses. In this case, it's the number 14. The standard deviation is the one that was stated. That's the 1.2. Our sample mean was 14.3. Our sample size was 50. And last but not least, this is extremely important. We now need to choose the appropriate tailness of the test. One of the things that you should notice is that all of these symbols that are being used here are ones that could only ever come from an alternative hypothesis. For this question, the alternative hypothesis was greater than. So we need to make sure we move the cursor over to greater than, hit enter to select it, and then we're able to go ahead and hit calculate. And whenever we hit that calculation button, that will give us that p-value. They ask us, typically we'll give p to 3 places. So this would round to 0.039. So p is equal to 0.039. Does anybody have any questions doing a z-test? Let's do a few more then. Let's take a look at number 7. In question 7, it says, suppose alpha is equal to 0.01. To test the claim that mu is less than or equal to 32 using a p-value, we are giving, again, the summary statistics. Find the p-value. To do this, let's begin by stating our hypotheses. We're testing the claim that mu is less than or equal to 32. That would have been a null hypothesis, which is the claim. The alternative is the opposite statement, which is going to be greater than 32. And then from there, we have the rest of the information that we need. Because n is 40, that's more than 30, or 30 or more, I should say, we will be using a z-test again. So we go back to the calculator. Again, we do stat. Go to the right option for z-test is the first one. The mu naught, that's the value using the hypotheses, that's 32. The standard deviation was stated as 4.3. X bar is 33.8. The sample size is 40. And now we need to make sure we're using the appropriate tail test. Here, this is yet another right tail test. Luckily, I already have it selected. And then we can go ahead and hit calculate. And to 3 decimal places, we would come up with a p-value of 0.004. So p for this problem would be 0.004. We're now going to take a look at example 8, where we're actually going to go through the entire hypothesis test. So we read through the problem and it says, a trucking company firm suspects that the average life of its tires is less than 34,000 miles. So that statement would be saying that mu is less than 34,000, which would be an alternative hypothesis. So for this problem, the claim is going to be the alternative hypothesis. The null hypothesis is the opposite statement. So that would be that the mean is greater than or equal to 34,000. Let's quickly kind of write down some of the other information we get. We go ahead and we take a sample of size 54, which in a moment we know is going to lead us to a z-test because it's a large enough sample. And we find that the average life of the sample, so the x bar value, our sample mean, is 33,390 miles with a standard deviation S of 1,200. And we are going to conduct our test at the alpha value, which is going to be 0.05. The only thing we need is, just like what we found with the last two questions, we need to compute the p-value. Once we have the p-value, which is the probability of our sample size, of our sample values, we're going to compare that to that value alpha, which is what was referred to as the level of significance. So it's kind of back to the calculator again. We're going to do a z-test with the given information. Stat, go over to test. We're going to do a z-test here. The mean and the null is the 34,000. Standard deviation was 1,200. X bar is 33,390. Our sample size was 54. And this was a left-tailed test. The alternative was less than. So we need to move over, highlight less than, hit enter to get that highlighted. We can now go ahead and calculate. We run our test, and we get a p-value like this. So One of the things, and I've seen in many years past, this will kind of throw students for a loop. P looks like the number 9.37. But after all, if you think about what P is, it's actually a probability. And we know that probabilities from back in chapter 3, probability is always between 0 and 1. If you go all the way to the right of this number, what you'll see is that it's actually E negative 5, which is scientific notation. So we have a p-value, which is 9.37 E negative 5. It's going to be helpful to write this number in standard form because we need to compare it to alpha here in a moment. E negative 5 simply means to take the decimal spot and slide it 5 places to the left. One place will move it around the 9. Because we have 4 more places to go, we would need to insert 4 zeros. Okay. And generally, we only want to round this to the first non-zero digit. So I would probably round it to 0.00009. So for this one, our p-value is 0.0009. And now that we've computed our p-value, we're ready to make our decision. This is very, very important. This is the entire crux for us of the p-value approach to testing. Please make sure you know this. So the hypothesis, the ultimate decision, boils down to this. If p is less than or equal to alpha, the decision is to reject the null. Anytime your computed p-value is less than or equal to the level of significance, the decision will be to reject the null. On the other hand, if the p-value is greater than alpha, then the decision will be to fail to reject the null hypothesis. So for us, this is how we were coming up with our decision to reject or fail to reject the null. It's all about the comparison to p to alpha. So please, please, please make sure you know this criteria. The other thing that I find is oftentimes very important for students is whenever you try to do this comparison, always try to get into the habit of putting p on the left side and alpha on the right side, just so you're kind of comparing them in the same order every time. That way it more easily matches up with this criteria that we have written down here. If we go to make the comparison, one of the things that we see is that 0.0009 as a number is definitely less than 0.05. So that means that we're in the case where p is less than or equal to alpha, and because of that, the decision would be to reject the null. So that is going to be the outcome of our hypothesis test. So to reject the null, the last thing we would want to do would be to state our conclusion. So let's go ahead and do that. And your conclusion has 2 parts to it. The first part is based upon the decision. Because we rejected the null, the first part of the sentence is going to go as, there is sufficient evidence to. So there is sufficient evidence to. And now the second half of our sentence depends upon which hypothesis is the claim. Anytime the claim is the alternative, the second half of the sentence goes to support the claim. So at the end of the day, what is kind of the takeaway from this? There is sufficient evidence to support the claim. The trucking firm suspected that their tires were getting less than 34,000 miles on average, and the evidence does show that that is indeed does seem to be the case. Whatever they're claiming does indeed appear to be true. And this is the entire hypothesis testing process from start to finish. You do your hypotheses, state which one is the claim. You then go to the calculator using either a z-test or a t-test. You compare your p-value. So you calculate that. P is then compared to alpha. That makes our decision. When P is less than or equal to alpha, we reject the null. If P is greater than alpha, we fail to reject the null. And then the last thing we want to do is write up our conclusion. Does anybody have any questions on problem 8? Let's take a look at another one of these. In question 9, it says a manufacturer claims that the mean lifetime of its bulbs is 1,000 hours. So they're stating that the mean is exactly equal to 1,000. So that would be our claim, is the null. The opposite of equal would be not equal to. We want to test the claim at the level of significance alpha equals 0.05. So that's going to be our level of significance. We need to compute P. To do that, we need our sample information. We took a sample of size 40. That's going to lead to a z-test here in a minute because it's a large enough sample size. The sample mean of those 40 bulbs was 980 hours, and the standard deviation of their lives was 80. So we have everything we need to compute P. We go back to the calculator. We go stat, tests, still using a z-test. The mean from the hypotheses is the number 1,000. The standard deviation is 80. Our sample mean was 980. Sample size was 40. And this was a two-tailed test because the alternative was not equal to. So we're going to go ahead and select not equal to. Go ahead and hit calculate. And we get a p-value rounded to 3 places of 0.114. So our p-value is 0.114. And now we're ready to make our comparison and our conclusion. 0.114 is greater than 0.05. So this produces a scenario where P is greater than alpha, and because of that, the decision will be to fail to reject. So fail to reject the null hypothesis. We're now going to go ahead and write up the conclusion. Because we failed to reject, the sentence will begin with, there is insufficient evidence to. And now the second half of the sentence will end, because the claim is the null, it'll end as to reject the claim. So this manufacturer claims that their bulbs last, in general, about 1,000 hours, and we don't have enough evidence to refute that. There's insufficient evidence that would disprove what they are saying. So, any questions on number 9? Let's take a look at the next one then. So in question 10, this is one that's a little bit different because we actually do have some raw data this time. It says a local group claims that police issue more than 60 speeding tickets. So as always, begin by trying to identify your null and alternative hypotheses. Here the null, they say more than 60. So they're saying that the mean is greater than 60 That would make that the alternative hypothesis, which is our claim. The opposite of greater than 60 would be less than or equal to. And this time we're going to test it at the 0.01 level. So alpha is 0.01, and we need to compute P. Instead of having the summary statistics, they give us the number of speeding tickets issued over the course of, I believe, what, 2 weeks? Yeah, so we have like, this is the number of tickets issued the first day, second day, third day. They do this for a total of 14 days. So our sample size is 14, which is small. That's less than 30. And because of that, we're going to compute P this time by using a t-test. Okay? So it's important to know why we're using the t-test, because we have a small sample size. The other thing that's different is because we have the summary statistics, we want to enter them into the calculator. So I'm going to plug in all of these numbers. We have 70, 48. Something happened here. So my apologies. 70, 48, 41. Just get them all in there. So once we have all of our data entered, if you wanted to compute things like the sample mean and the sample standard deviation, you could always go back to our good old friend 1var stat. So hit the stat button, go ahead and hit calculate, hit 1var stat. Make sure you're using only list L1. And that will give us the sample mean, excuse me, and make sure you're using the sample standard deviation here, which would be the 13.43. Alternatively, you don't really even need to do that. When we go to stat, when we go over to test, t-test is option 2. So we hit enter. And now we can work right off of the data tab. So I'm going to move my cursor over to data, hit enter. And now I can enter my information. The value that was used in our hypotheses, that was the number 60. So that goes here. And there's a place for us to tell the calculator that we're using all of the data off of list L1. So just make sure list L1 is in there. Frequency for this menu should always be set to 1. And then just choose the appropriate tail test. This time it's going to be greater than. Go ahead and hit calculate. And we get our p-value to 3 places would be 0.477. So P is 0.477. We're now ready to make our conclusion. Comparing these two numbers, 0.477 is greater than 0.01. So we're in the case where P is greater than alpha. So the decision should be to fail to reject the null. So fail to reject the null. We can write our conclusion. Because we failed to reject the null, the sentence will begin with, there is insufficient evidence to and now for the second half of the sentence, we need to see which hypothesis was the claim. Because the claim is the alternative, the second half of our conclusion needs to end with to support the claim. So there is insufficient evidence to support the claim. So this individual, this group that's claiming that police are issuing more than 60 speeding tickets in that area, based upon the data, the sample size that we've collected, the data does not support their claim. There is insufficient evidence to support the claim that they're issuing more than 60 speeding tickets a week. Or perhaps a day, it should be said. Any questions on number 10? We now move into the linear regression material. So typically, when it comes to like correlation, positive correlation, if you remember like your information from like, I don't know, like linear algebra or like basic algebra, positive correlation means that the best fit line would have a positive slope. The best way to think about two variables being positively correlated is that they have the same behavior, meaning that when one variable goes up, the other value of the variable goes up. And if one's going down, then the other one also goes down. When two variables are negatively correlated, they have opposite behaviors, meaning that as one value of the variable goes up, the other variable will decrease, and vice versa. And then if the two things are completely unrelated, then we would just say that there is no correlation. Okay. In question 11, it says, given the supply of a commodity and the price of the commodity, would you expect a positive, negative, or no correlation? For this one, it's kind of easy to think about it if you think of like, whether you think in terms of scarcity or whether you think of perhaps in terms of like the Walmart effect. The more of something you have, the more readily available it is, the less its price is going to be. So the more supply of something you have, that will decrease the price. So when commodity supply goes up, price goes down, that means that the two variables are doing opposites. So that would be a negative correlation. In question 12, if we measure the length of someone's femur, which is their leg bone, compared to their humerus, which is their arm bone, would you expect a positive, negative, or no correlation? Well, typically the larger somebody is, the larger their leg, and consequently the larger their arm would be. So when someone's femur gets longer, their body in proportion would get larger, so too would their arm. So when one increases, the other would also increase. So those two variables should be positively correlated. Does anybody have any questions on positive, negative, or no correlation? For the next question, we're going to get into the scatter plot data. In order to do a scatter plot, so even before doing that, one of the things that hopefully you all have done by this point is turn your diagnostic tool on. We need that to compute the R value in this chapter 9. If you haven't yet done this, this is just a one-time thing you need to do. We need to go into the catalog of the calculator. You hit the second button, and then you hit the number 0. In the catalog, you're going to scroll all the way down until you come across the option Diagnostic On. So there's two choices, off and on. We want to make sure our diagnostic is turned on in our calculators. So you highlight that, hit enter first. That will put that onto your home screen. You now need to hit enter a second time, and now it should be ready to roll. So now it's turned on. You only ever have to do that one time. The second thing we want to do is, because we want to do a scatter plot, we need to turn our scatter plot on, or our stat plot on in our calculators. To do that, we need to hit the second y equals key, which will bring us into the stat plot menu. So I hit second, y equals, and I want to turn just one of the plots. I want to turn plot 1 to on. So right now it's turned off for me. So I'm going to hit enter to get into that menu. And I want to toggle it from off. I want to put it to on. So I hit enter. The type of graph we're doing right now is simply going to be a scatter plot. So the first option should already be highlighted. The X list should always be L1. The Y list should always be L2. And then you can visually kind of choose which mark you want to show up when it graphs it. I typically find that the first one is the easiest to read, so I wouldn't change the visual display there. Just leave it as it is. And now what we're going to do is we're going to enter our data set, the X values. So all of these X values here are going to go in list L1. All of the Y values are going to go into list L2. So I hit edit. I'm going to go ahead and clear this off. And now I'm going to input my X values. So -5, -3. When you're putting your negative numbers in, make sure you're using the negative symbol down here. Don't use the subtraction symbol. You'll get a syntax error. Then we have 4, 1, -1, -2, 0, 2, 3, and -4. It's now very important. We need to go into the L2 list and put the corresponding values for Y directly beside them. So the first X value was -5. That corresponded to a Y value of 11. Okay. You must put them in order. You cannot sort any of these lists or it'll totally throw off your order pair. So just plug them in as you see them. And it looks like I'm missing something. Nuts. It's gonna be 1 second, everybody. Might have had a data entry error here. So that looks good, good, good. 2, 3. Something happened with my L2s. 11, 6, -6, -1. The next value should have been 3. So 3, 4. 1 goes with 0, -4, -5, and 8. That should do it. Give everybody another couple seconds here. See if you can get those entered if you're trying to follow along.
I'm pretty sure somebody asked how it would look on the T83 calculator.
Yeah, excellent question. So the input, it should look identical. So on the TI-83, in terms of these menus, you'll have exactly the same setup, exactly the same information. Excellent question. Thank you for noting that. Yeah, this is one area where those two calculators will be identical in terms of the input and the screens. The next thing we want to do is we're actually going to go ahead and graph this. Now, once you have those data points entered, and as long as your stat plot is on, we can go ahead and hit graph. Okay. Now, I have a bunch of stuff in here from before. Sometimes students will get like an error message. If you have an error message, just make sure you go to your Y equals menu, clear out anything that you might have already put there, because you don't want that to kind of be in there. And then oftentimes too, so I'm kind of lucky here that these data values show up when I just hit the graph button. Depending upon your scale or the numbers, what I always recommend for students to do is do a zoom stat. So anytime you do a scatter plot, if you do a zoom stat, the calculator will fit it in the nicest window possible so that all of your data points show up. For this kind of a question, it's designed so you should all be able to just kind of look at it and tell the type of correlation. We will be moving on though in a little bit where we have to calculate the Pearson R value, and that gives a measure of the strength of the linear correlation. But for this one, I think all of us can just look at it and see clearly that because the line is moving downward, like a negative slope line, this would be two variables that have a negative linear correlation. Does anybody have any questions on this one? Let's take a look at the next one then. It's kind of the same deal. It says data below shows the gestation periods in months of randomly selected animals and their lifespans. They want to do a scatter plot for this and determine what type of correlation we might have. So I go back into the stat menu. We're going to go ahead and just clear out all of our data from before. And let's enter this data set. So we have 8, 2.1, 1.3. That's all my x values. I now come over to y2, and in order I need to put the y's. Again, once you have that done, we're going to do the same thing. I'm going to graph these. As you can see, when you first hit graph, only a few of the data points show up. Because we've entered new data, we need to do a new zoom. So we're going to go back to zoom. Go down till you find zoom stat. Should be option 9 on both calculators. Hit enter. And now it shows the window in a much nicer format. And what we can glance off of this is that the data generally seems to be going up. So as we go to the right, the data is moving up. So any potential line of best fit would be positively sloped. So we would describe these two variables as having a positive linear correlation. So positive linear correlation for these two. In 15 and 16, they ask us to identify the independent variable and the dependent variable. In general, the independent variable is kind of the one you can think of that you can kind of control. And the dependent variable is the one that depends on what kind of the independent variable is. For example, if you look at the rainfall in inches used to predict the yield per acre on a wheat farm. So a lot of times I'll ask students this question: which one depends upon which? Does the rainfall impact how much wheat we get, or does the wheat impact how much rain we get? And the answer is it's the rain that impacts the yield per acre. That would make the rainfall the independent variable, and the yield per acre, that would be the dependent variable for this question. For the next one, it says determine whether the number of hours spent studying for a test can be used to predict the grade on the test. Here, the independent variable would be the hours spent studying. So that's independent. And then the thing that would depend on that would be your test grade. So the grade on the test would be the dependent variable. In question 17, we now move on to information about the Pearson R value. It says, suppose we had a data set that had an R value correlation coefficient of negative 0.991, and the B value had a coefficient of R equals positive 0.991. Which of these statements would be correct? A is stronger than B, A is weaker than B, or A and B would have the same strength? The answer to this is going to be C. They have the same strength. And the reason for this is you need to compare not just the values of these two, but you need to compare their absolute values. The larger your R value is, the greater the overall strength of your linear relationship. So first thing, R itself, always varies in between -1 and +1. If you had an R value of -1, that would correspond to a perfect negative linear relationship. And at the other extreme, if you had R equals to +1, that would be a perfect positive linear relationship. Okay. Meaning that for R equals to -1, all of the data points would lie on a single line that has a negative slope. And if R is equal to +1, then all of the points would lie on a line that has a positive slope. And then you get varying degrees of strength of the relationships. But the closer they are to either -1 or +1, in general, the more powerful they are. So if we're asked to compare two things like this, so data set A had this R value, data set B had this R value, to see which one is stronger, you need to compare their absolute values. The absolute value of -0.991 is positive 0.991. And likewise, this has absolute value equal to 0.991. And because they have equal magnitude, we would say that those two data sets have the same strength of linear coefficient. This one in A is as close to being a strong negative linear correlation as what the data set in B would be, comparing it to a strong positive correlation. So there the answer is they have the same strength. As a follow-up to this, question 18 says, which one could not represent a correlation coefficient? Well, remember, correlation coefficients always have to be between -1 to 1. So this is allowable. B would not, because it's more than 1. C would work. You could have a value of -1, and D would also work. You could have a value equal to 0. Okay. So the answer to this one would be B. Can never be more than 1, can never be less than -1. Question 19 gets us into finding the equation of the linear regression line. This is the last calculation button you need for the test. So it's going to begin the same way. We want to enter our data set. So we go to the stat menu, go to edit. Once again, the X values will go in list L1. The Y values will go in list L2. So we want to kind of go ahead and get them all entered. From there, we're going to go over to stat. We're going to go to calculate. And this will be the same on both the 83 and the 84. We are always going to make sure we use option 4. So it's stat, go over to calculate, and choose option 4. It should be linear regression AX plus B. We hit enter. On the TI-84 and the 83, there will be a little bit of difference this time out. The 84 will prompt you for X list L1, Y list L2. Frequency list should always be blank. And there's the option to store the regression equation. We're just going to go ahead and hit enter. On the 83, you should be able to go ahead and hit enter and end up at this screen right here. Okay. The regression equation, they actually give it to us in terms of the formula. It's Y equals AX plus B and then directly below they tell us what the value for A is and what the value for B is. So I'm going to copy this down. So this is the equation of our regression equation. It's going to be Y equals, and for the test it'll say to round it. I'm going to round my coefficients to 3 places. The A value to 3 decimal places would be 2.097, and that A is multiplying to X. And now we need to add B. B is a negative 0.552. So 0.552. And that right there would be the equation of our regression equation. Does anybody have any questions on using the linear regression tool to find the regression equation? So if nobody does, 20 and 21 are the same. So I'm just going to kind of skip those. The solutions are on the D2L. Let's look at 2 more though. Question 22 says, given the equation of the regression line, y hat equals 2x minus 5, what is the best predicted value for y given that x equals to 10? So with this problem, we want to forecast or predict what y is going to be when x is 10. This is literally just direct substitution from algebra. If the equation is 2x minus 5, then everywhere we see an x, we're going to put 10. So it's going to be 2 times 10 minus 5. Use your good old school order of operations. Multiply first. That's going to be 20 minus 5, which is 15. So when the value for x is 10, the corresponding predicted y value would be 15. We now will kind of go ahead and take a look at 23 and 24. These would be the last 2 that we do. And here it says, use the regression equation to predict the value for y when x is 2.2. It's more or less the same thing we just did a moment ago, but before we can do that, we first need to come up with the regression equation. So we need to come up with that regression equation, which is y equals ax plus b. So we're going to go ahead, we're going to edit and put our data in here. So x is negative 5, negative 3, 4, 1. Now our y values go in L2. So now that I have them in, once again, what we're going to do is we're going to go to Stat, Calculate. Option 4 should be linear regression. That will give us the equation. We can now go ahead and write down the equation. The thing that's nice is they remind us the form of it. So again, it's y equals ax plus b. For us, we're just going to write the coefficients to 3 decimal places. The value for a is going to be 2.097 x, and then b, if I was probably paying attention, this is the same data set we had a minute ago. But here we are. So we have our regression equation, and all we want to do is now substitute in x equals 2.2. So everywhere we see an x, we're going to plug in 2.2. So let's work that out. So 2.097 times 2.2 minus 0.552 would give us a predicted y value of around 4.061. So the predicted y value would be 4.061. One of the things you have to be very careful with, and this was in the homework, and you will see this on the exam, is that whenever we're doing a linear regression, okay, the values for which that equation is valid is what we call the domain, meaning our linear regression only holds up within the range of x values that we have. If we look at the x values that we are given in the table, the smallest x value was -5. The largest x value we had was +4. That's what we would call the domain of our regression equation, and that's very important. What that means is that these are the values of x that we can reasonably plug into this equation and expect to get an accurate prediction for y. Okay? Luckily, the x value we were using, which is 2.2, fell inside of that range. So because 2.2 is greater than or equal to -5, but yet less than or equal to +4, it's inside that domain. We are allowed to plug this in, and we would feel confident that our prediction would be in the ballpark. If somebody came along with the same question and said, oh, can you predict the value for when x equals to, let's say, 11, then the answer we would say would be, you could say not in the domain, or you would not be able to do it. Because at that point, the value x equals to 11 extends so far outside of our data set that we can't trust that that relationship would continue on indefinitely. So it's a good idea that whenever you try to go ahead and do this, that you check to see that the x value you're plugging in is in the domain of your function. One of the other things I wanted to bring up too that would help you with the 9.3 stuff is whenever we calculate that linear regression, because you all would have had that diagnostic tool turned on, that also gives us the Pearson R value, by the way, which is down here, the 0.989. That would be your Pearson R value. And then the coefficient of determination, the thing that we call it R squared, that's literally directly above it. That's the 0.979. So if you're ever looking for the Pearson R value, the correlation coefficient, or the coefficient of determination, R squared, those are both highlighted when we do the linear regression. Take a look at one more. Let's do maybe 24. We want to do the same thing. We want to do a linear regression, and then we're going to do a prediction for when x equals to 11. So enter the x values first: 0, 3, 6, 4, 9, 2, 15, 8, and 5. And we have 98, 86, 80, 82, 71, 92, 55, 76, and 82. We do stat, calculate linear regression, and that should give us our coefficients of our regression equation. So our regression equation for this problem is going to be y equals a, which is -2.755 times x plus b, which is 96.139. Before I do any forecasting, let's just do a quick check of the domain. For the domain, you're just looking at what is the smallest x to what was the largest x. Here, the x values range from 0 to 15. So this regression equation, the one that we just computed, we would be allowed to plug in any value of x that falls between 0 to 15. Because of that, x equals to 11 is inside, so we can forecast this. Okay, I think the phrase that they were using in the notes or in the My Stat Lab was the phrase "not meaningful," right? So if you try to plug in -2, or if you try to plug in 20, you can say "not in domain." You can also use the term "not meaningful" there as well. Everywhere we see an x, we're going to put an 11. We can just throw that into the calculator. -2.755 times 11 plus 96.139. When we hit enter, this would give us a y value of approximately, 65.834. So about 65.834. And of course, the r squared and r, if you wanted those two values, they're listed as well. But this problem did not ask for that. Another way, so especially with the exams, you can get partial credit by showing this work. If you wanted to do that, let me just finish with this really quickly. There's a slick way to do this. If you also, when you do your stat and calculate linear regression, if you wanted to store your regression equation into the calculator, what you would do is you would go to store regression. This is on the 84. You would hit vars, go over to yvars, hit function, and then I'm going to store it in y1. I can go ahead and I can hit calculate, and it does exactly the same thing as we saw it do a moment ago. But in addition to that, if I look at my y equals menu, the calculator will automatically store that in the calculator for you. The convenience this will have for us if I do this, if I do a zoom trig, not a zoom trig, zoom stat, there it is. It'll not only plot the data set, but it'll also plot your line of best fit. And then a simple way to do this forecasting is you just want to evaluate your regression equation at 11. I can use the second calculate button, value, and then plug in literally x equals to 11, and the calculator will do that for us. So 65.836, well, we got 65.834 because we rounded a little bit. That value would actually be a little more accurate. So once you get the line graphed by doing the zoom stat, you can use the second calculate trick for value if you've already stored your equation under the Y1 menu. You can also get the calculation without even having to go to the graph by doing the following. You can go back to vars, go over to yvars, function y1, put it on the home screen, and then put a parenthesis around an 11, and then the calculator will automatically compute y1 evaluated at 11 if you hit enter. So if you like this method, you can do that. It's a little bit of a time saver, but just plugging it in directly isn't that hard either. Does anybody have any questions on the test review? If not, that's all I have. Have a wonderful evening, everybody. Good luck on the test tomorrow. If you have any questions, just please let me know.
Thank you.
You're welcome.